Hey, jullie zijn er weer, of nog?
Ik ben er in ieder geval weer.
Je hebt een prachtige tuin.
Dankjewel. Ik zit eigenlijk ook hartstikke lekker. Dat ik net in het zonnetje was, misschien een beetje warm.
So do you know how many of you are English speaking? You never met, huh, in your class? I have no idea.
Yeah, no, not yet. So for the biophysics people, at least a group of us will meet up on Wednesday, which will be the first time for most of us.
Okay.
So I'm quite looking forward to that.
Yeah, I can imagine. How large is the biophysics group?
So it should be 11 people.
And then the medical natural sciences, although it has a new name now, that's then about 20?
I think
biophysics were with 9, right?
Oh, was it 9? All right.
Yeah, I thought so.
Okay. Normally when I give my class, I ask you from which universities you were coming. Is it predominantly the UvA and VU, or also in the neighborhood of Amsterdam?
Yeah, I'm from Leiden University, but I've heard quite a lot of people coming from Amsterdam.
Okay.
One Delft here.
Delft, okay. Is that Boer? Yeah, okay. And from abroad, outside of the Netherlands? London, okay. Oh, London too. 12 zijn er related, okay. All right, let's start again. So I did a lot of the theory and I'm gonna just describe more. Show you more Jablonski diagrams. So this is another Jablonski diagram for the Rayleigh scattering. Incident energy is equal to emitted energy of the photon, and this is an energy that's a photon of a longer wavelength that's emitted, even longer and even longer, corresponding to exciting this vibrational level in the molecule. So it's a very rare process, Rayleigh scattering. In other words, it's very inefficient. And I will give you numbers to get a feel for how inefficient it is compared to Rayleigh scattering. Like I said, we also have the anti-Stokes scattering, which means that we use the energy of the molecule, vibrational of the energy, to emit a photon of a higher energy or shorter wavelength. So this is a molecule in an excited vibrational state. This is just classical, the standard Rayleigh scattering. But this here is when we emit a photon of a higher energy or shorter wavelength. It's the anti-Stokes process. And we can get photons of higher and higher energies. For instance, if we already in this vibrational level, we excite here to what we call this virtual state, we fall down to the ground state and we get a photon of an even higher energy that is emitted. The reason that you can have this anti-Stokes scattering is because molecules are already in a vibration state, higher energy state, vibrational level, and most common then is that is due to the temperature. So, for instance, if you look here at the spectrum of silver, we see on this side here the Stokes shifted light, and on this side we see the anti-Stokes shifted light, where you can see that the peaks here are much smaller. And so to get an idea, so if you have the occupation, the thermal occupation of vibrational levels, N1 versus the ground state is governed by this equation, Boltzmann equation, and so it's given, the occupational level of N1 is given by the exponent of minus the energy difference divided by KT, and KT being then the temperature. And then as a rule of thumb for room temperature, KT is about 200 in per centimeter. So let's say from 0 to like the 200, you can expect to see anti-Stokes shifted light due to thermal excitation at room temperature. To give you an idea of how efficient Raman scattering is, so if you look at just standard scattering, Rayleigh scattering in the IR in tissue, then the scattering length μs prime is on the order of 1 millimeter. That means a photon travels approximately a millimeter before it's being scattered. If you look at absorption in the near IR, then a photon travels about 10 centimeters before it's being absorbed. If we look at the absorption of red light in water, then it's about 5 meters before a red photon gets absorbed. But if you look at Raman scattering, the probability for a photon to be Raman scattered is on the order of, well, it means that the photon has to travel about 3 kilometers before before a Raman scattering event occurs. And if you look at these numbers here, you see that most likely that photon is already absorbed before it can be Raman scattered. So that Raman intensity is really, really low. It's very weak. If you want to express it into scatter cross sections, then the cross section for Raman scattering is about 10 to the power minus 30 square centimeters. Another way of looking at this is 1 in 100 million photons are Raman scattered. Oh. So that was, of course, a big problem, that the Raman effect is so inefficient or has a very low probability. So in classical Raman spectroscopy, before the occurrence of the laser, you required very long exposure times and high concentrations of your material. With the laser and with the more efficient detection, it has become much easier to measure Raman spectra. If you then look at how does the Raman intensity or the probability relate to the excitation wavelength. So the intensity of the Raman scattered light depends on K, on the incident intensity in a linear manner, on the polarizability of the molecule, and on the frequency to the 4th power. And this is equal to what you have seen for scattering, that the scatter cross-section of a point scatterer is proportional to the frequency to the 4th power or 1 to the wavelength to the power 4. That is the efficiency of Rayleigh scattering, and this is also an explanation of why the sky is blue. I'm pretty sure Dirk has explained it or will explain it. But that same relation holds for the Raman intensity, and what it means is that you can get more Raman scattered light. Sky, check, good. Lambda over 1 over lambda to the power 4, check. We'll find out, check. So the process is more efficient for shorter wavelengths. So it pays off to illuminate something in the UV. Then the Raman effect will be stronger. Actually, it increases with the, to the power 4. So there's a lot to gain to go to the UV. The downside in biological tissues is that UV doesn't penetrate very deep in biological tissue, and if you look at in vivo tissue, around the wavelength of 350 nanometers and 330 nanometers, you run into the risk of direct DNA damage. So you definitely want to avoid that. The polarizability of the molecule can be influenced by resonant Raman scattering. I will show that a little bit later. Despite this higher efficiency at shorter wavelength, most experiments are still done at a longer wavelength, and I will also show you why that is a good idea. So this is the Jablonski diagram for conventional Raman scattering, where we use an excitation wavelength that is below the first excited state, electronic excited state of the molecule. For resonant Raman, we use the fact that there is an electronic excitation, and so we use a photon that actually is somewhere in this electronic excitation band, and then from here we fall down to this vibrational level here. And it turns out that just the presence of that electronic vibration makes the probability of this process much likelier, and it has to do with the polarizability. Sorry, I see a message that I don't understand, but that's fine. That has to do with the polarizability of the molecule. Another main problem for Raman scattering is the background fluorescence. And so if you excite a compound or a fluid with a laser, you also get a fluorescent background, and that fluorescent background can show up on top of the Raman spectrum, and especially if because the Raman spectrum is weak, the fluorescence can really overwhelm the Raman signal. And so if we then look at the different excitations that are possible, we have excitation in the UV. We have even UV resonant excitation, so we make use of a really high electronic excited state in the molecule to enhance the Raman effect. We can use visible excitation, where we use another electronic level in the molecule, and we can use near infrared excitation. So if you look at the UV resonant excitation, we excite to an electronic level here. It decays to a ground state in S1, and from S1 we get a photon emitted to the ground state or to an excited state of the molecule, vibrational level. If you look at visible excitation, we have sorry, I'm making a mistake here. This is not a Raman signal, this is fluorescence. So this creates now a fluorescent background. What you have to realize is that this particular fluorescent background is of a completely different wavelength than this Raman signal. You can see this Raman signal is a significant energy difference, so it's a very short photon. The photon from the fluorescence is of a completely different wavelength. If you now look at the Raman signal for visible excitation, we excite to here and this is the Raman photon that's being emitted. If we compare that to fluorescence, where we just excite the electronic state, we have non-radiated decay to a ground state in the S1 band, and then we fall down into the ground state. We see that this fluorescence is approximately of the same wavelength as the Raman shifted photon. And so in this case, the Raman spectrum is going to be overwhelmed by the fluorescent background. If we go to the near infrared excitation, we excitate here to a virtual state in between these two electronic bands, and we fall down into the excited state of the molecule. We get a Raman photon, and we don't get fluorescent background. But you know, this is a very inefficient process. On the other hand, you have a much lower background, and so in general, this still wins out when you use it in biological applications. Okay. Some of the, well, the downside, the disadvantages I discussed. The advantages of Raman spectroscopy is that it's broadly applicable. Most materials have molecular vibrations. You can measure in situ, which means even from a distance. You can, with a laser, excite tissue, you know, that's centimeters away and collect that light. So it's kind of a non-contact method and non-destructive. It gives you molecular information, so you're able to identify molecules. You also can say something about the environment, for instance, acidity or temperature. Very little sample preparation required, and there's also very little interference from water. I showed you two spectra already, cholesterol and sulfur. I'm going to show you three more biomolecules. That is glucose, creatinine, and lactic acid. Just for you to get an idea of what spectra look like, and they're all in this wavelength band from, let's say, 600 to 1600 inverse centimeters. This is what is called the fingerprint region for these biomolecules. If you want to use this for biomedical application, it would be nice if you can build it into endoscopes, and so therefore you would like to use fiber optics to deliver the light and collect the light. One of the main problems with using fiber optics is actually that the light has to travel through a fiber, and the fiber itself creates a lot of background. Let me see if I have one. Is it present? Here. This is the signal that you get. Along this axis is inverse centimeters, so this is the energy axis here. And this is the intensity that you measure. This is just sending light through a silica fiber. And you can see that it creates a huge background in this really relevant region of, let's say, 600 to 1600 inverse centimeters. So the fiber is long, 1 meter, 2 meter, maybe even 5 meters. So you have a lot of interaction length where you're creating this background. And then the measurement volume in the tissue might be, half a millimeter in depth or less, where you collect your signals from. So these long fibers really pose a problem. They create a lot of background. And so if you want to avoid that, you have to really carefully design your probes. And for instance, this is an example of how you would do that. You take your excitation fiber here in the center, and you take your collection fibers around that center fiber. So this means that you have a fiber bundle of, let's say, 7 fibers in this case. You excite through the core, and you collect through these side fibers. And then you have to carefully filter the light. For the excitation fiber, you want to filter out any light that is created on the way to the fiber tip. So you want to have a very narrow transmission filter. So this is a very narrow transmission filter that only passes the excitation wavelength of the laser, and all that fluorescence that was generated in the fiber on the way to the fiber tip you block. And then On the collection side, you want to really block your excitation laser. You don't want any of the excitation laser entering your collection fiber, because on the way back, that intensity, that Rayleigh scattered light is intense. It's probably going to create more fluorescence. You don't want it, so you want to block it out, block out the excitation laser, and only measure then this part, the Raman shifted light. Let me see, I think I'm gonna skip this one and go to a different process. So I explained normal Raman, I explained anti-Stokes scattering, and now we want to go to a process that is called coherent anti-Stokes Raman scattering. And the idea is that you want to increase the sensitivity and you want to decrease the background. And so one of the more complicated schemes that you could use to measure now these vibrations in molecules is use an excitation laser, this one, and then you get a Raman scattering to this excited level. Then you provide another photon that excites it, and then you fall down to the ground state. And now you have created an anti-Stokes Raman scattered photon. And what is the nice feature of this anti-Stokes Raman scattered photon? It has a higher energy than the incident light. And so all your fluorescence light and other kind of background you can eliminate, because the detected photon is of a shorter wavelength than your excitation photons. The trick here is that you drive this process with a separate laser, and by providing both this excitation light and this wavelength that matches the Stokes frequency, you can increase the efficiency or the probability of this process significantly, which means that you kind of force this population excite again and fall down. So in words, the energy between the two photons brings the molecule in a vibrationally excited state. In my next slide, I will make it more likely that this happens. So to arrive here, you need 3 photons, 3 fields, and this is the field that's being generated when you fall down from this virtual state to your ground state. The advantages of coherent anti-Stokes Raman scattering are that they're more sensitive, so the signals are stronger than spontaneous Raman, so the likelihood is much higher. It's nice to implement into microscopy. It's being used a lot for real-time imaging. The contrast of the signal is based on vibrational characteristics, so properties of the molecules. There's no need to tag a molecule with a fluorophore. It has a signal at the higher frequencies or the lower wavelength, which means minimal fluorescent interference, and it has a higher resolution because it turns out to be a non-linear process. And so now to this idea as to, how is it possible to force this molecule into its vibrational state with 2 incident photons? Stimulated emission, yes, it comes close to that. So you provide 2 photons. You provide this pump beam, and you provide this Stokes beam, and these are electric fields that oscillate rapidly. And so if you look now at the beating between these electromagnetic fields, then you create a beating on the difference frequency. And this beating on the difference frequency is now exactly at the frequency of the vibration of the molecule. So this is how you force more or less this molecule into its vibration. And having it in this vibrational state allows you now to excite it with your 3rd photon into a higher virtual state and falling down into your ground state, creating that anti-Stokes shifted photon. Okay, the derivation of the probability is the same as we did before. We were analyzing Raman scattering by looking at this dipole moment of the molecule, and we used the first order to explain the classical Raman process. But we can write an expansion. We can take the polarizability, the second order polarizability, multiplied with the square of the fields, or basically the product of two incident fields, and we can describe it with the third order polarizability multiplied by three incident electric fields, or field to the third power. So the Cars process is this third order process, because I said we need one photon, we need two photons to force the vibration, we need the third photon to excite it and get the vibration state to a virtual level, and then we fall down into the ground state, and that's the emitted photon or the emitted field. So this anti-Stokes polarizability, or how the dipole moment oscillates as a function of time, is given by these two pump photons, two pump fields and one Stokes field. The dipole moment generates an electric field that is not yet an intensity. The intensity that we measured is given by the emitted field squared. So if you want to know the intensity of the anti-Stokes shifted photon generated by this dipole moment that we have introduced in the molecule, then we need to square this part here. So that means we get the pump power squared and the Stokes beam power in a linear. So it becomes a third order process, or depending on intensities to the third power. In other words, the Cars signal depends quadratically on the pump and linearly on the Stokes beam intensity. And since it's a non-linear process, this process really benefits from pulsed lasers, because if you do it with a CW laser, you have a constant power. But if you pack all that power into a very short time, you get a very high peak intensity. And since it goes with that peak intensity squared and here linear with this one, you increase the efficiency of this anti-Stokes emitted light significantly by using pulsed lasers. There's one more thing, and I will only explain this to the light tissue interaction students, and that's the fact that all these molecules are in phase when they vibrate, and this creates a coherent amplification of the field that's being emitted. I will leave that for one of my later classes that we will do separate. Anyway, so we need pulse lasers, we need these pulses to overlap, and that is quite a challenge. We have, for instance, a pump laser here that has a repetition rate of about 80 megahertz or 76 megahertz, and we have a pulse length of about 7 picoseconds. But for this process to take place, we need a second laser, which we can tune to that particular Stokes shift that we want to observe. It has to have the exact same repetition rate, and in that pulse train, this pulse has to overlap exactly with this one, because if they don't arrive at the same time in the tissue, the three photons are not present at the same time and nothing will happen. And so it requires a careful delay between the two lasers to create this overlap. And moreover, you cannot just use two lasers that pulse at 76 megahertz because there will be very tiny frequency differences, and these frequency differences lead to a drift between these pulse trains, and it's very unlikely that you get perfect overlap between these pulses. And so there's a very nice way of doing it, and that's called with OPOs, optical parametric oscillators. I don't think I have it in here. No, I don't. Sorry. Just to explain, what you do is you take a photon, you send it into a crystal, and this crystal breaks that photon up into two other photons. And these two other photons are of different wavelengths. The nice thing is if you send in a pulse, it breaks it up instantaneously. And so the broken up pulse, the two new wavelengths that you send out, will pulse at the exact same time as your pump. So if you take this laser beam from your big pump laser, you send it to the OPO, it will create pulses of light that are exactly synchronous with your pump beam, fluctuate in the same way, and you can create a perfect overlap by introducing the proper delay line between the powerful pump and your Stokes beam. So it is possible to create really nice overlap between these beams. Then the question, should you use picosecond or femtosecond pulses? I think we all know the relation between the duration of the pulse and its frequency content or color content. In other words, if the shorter the pulse, the broader the spectrum that is in that pulse, or the different frequencies that are in that pulse. And so you can imagine now that if you make a really short pulse, that it can have a bandwidth of tens of nanometers in the spectrum. But we also know that the Stokes shifts, and that was the exercise you had to do, these Stokes shifts, the width of a vibrational level is very small, few nanometers. So if you excite with a laser that has a spectral width of tens of nanometers, and you want to measure a line width of a few nanometers, that you're doing that in a very inefficient way. You actually create a much broader response than is required. You measure much broader spectrum than is emitted by the Raman process. So ideally, you would like to match the pulse length of the laser in such a way that the wavelength content or the frequencies that are present, the bandwidth in color, so to speak, matches the bandwidth of the vibrational level. And that means that you look particularly at picoseconds, 5 picoseconds pulse lasers. I'm gonna also skip this one. What I want to get to is a study that we did in zebrafish, and we used even another process for it. And this is a very this has become actually the dominant way of doing stimulated Raman scattering. So cars has gone out of fashion lately. I think this is the more dominant way, and it works in the same, more or less in that same way as that how you excite the molecules in the vibrational level in the cars process. So what we do here is we provide two photons. We provide a pump beam, and we provide a Stokes beam, where the frequency of the Stokes beam matches the difference between the pump beam and the Stokes beam matches this vibrational level. And so what happens now, that's a dove. Where was I? Okay, so when we have the molecule present, then the likelihood exists of exciting to a virtual level and falling down to this vibrational level. if we have both beams present at the same time, then if this level is present, the intensity of the Stokes shifted light will increase. If there is no vibrational level, then the intensity of the Stokes... I'm sorry. She's loud. Okay. So when there is no vibrational level present, what we will measure here is just the intensity of the laser beam that we send in. But if this vibrational level is present, we have the probability of this Raman process, so the intensity of this beam will decrease. And so what we do is that shown here? No. There was a possibility that it shows an animation where we start to modulate the pump beam. So we turn this pump beam on and off. And when there is this vibrational level and the pump beam is on, then this beam will have a higher intensity. And if we turn it off, there will be a lower intensity. So we modulate the pump beam, we measure the Stokes beam, and if there is a vibrational level present, the Stokes beam is going to be modulated, and if it's not, it's going to be absent. And so by measuring these tiny fluctuations in the power of the Stokes beam, we can determine if there is a vibrational level present. This is called stimulated Raman scattering. It's a fairly, well, not fairly easy, but this is the kind of setup that you would use for it. You use a pump laser. The pump laser light is used to be one of the two beams that you put in. This is the optical parametric oscillator that generates a second wavelength. You combine these two, go into a microscope, you rapidly scan the surface, and then you can look whether or not one particular vibrational level is present in your biological sample. And so if we do that, we look, for instance, at lipids in biological tissue, then we're particularly interested in the CH2 stretch modes of lipids. So this is a way to determine whether or not there's fat present. And there are many of these CH2 bonds present in a cholesterol molecule, in a lipids. So it provides a very strong signal. And what we did with it was determine how a diet influences the fat deposits in the zebrafish. So you take these tiny zebrafishes, you put them on a diet, you put them on a normal diet, on a high fat diet, and on a high glucose diet, and you measure their storage of fat inside of their body. So if you look at this image of the zebrafish, then this location is where you have the adipocytes, that is the fat storage. You can measure then the size with this stimulated Raman scattering, and then you find as a result that indeed on the high fat diet, the fat storage is much higher in these zebrafish than if you put them on a normal diet. Well, this is to be expected, but there's one interesting thing. If you feed them a normal diet, and now you disturb their circadian rhythm, their day-night rhythm, which is a crude way of kind of forcing jet lag in these zebrafish, it has the same effect as being on a high-fat diet. And so this is interesting that you can then demonstrate directly a relation between disturbing your natural rhythm, you know, being jet lag or being on a night shift roster, how that actually influences your metabolism, that even on a normal diet you have a propensity to store more fat in zebrafish. Okay. So with that and with these kind of applications, I would like to conclude this lecture, and I'm open to remaining questions if you have some. No more questions? Okay, I will see you again on Friday. And then we'll do the first course of OCT. Dirk.
Yep. Very good.
Bye-bye.
Okay, yeah,
I'll
thanks.
take care of the recording. Thank you very much.
Okay.
Yeah.
And see you all on Friday.
Okay,
Bye.
Bye.
You.
take care.